He gave us 8 books today.
All right, welcome everybody. Thank you for coming to Math Club today. We are lucky to be hearing from Fabrice Razafimahatratra today, who's going to be talking about the work of Grothendieck. So take it away, Fabrice.
Just practice that. Thank you, Jared. You're among the first few people that can't pronounce my name in public. But yeah, so I'm gonna have like a short talk about Grothendieck, and then we're gonna move on to like some fun with math Jeopardy. So this is my first time doing this, so it's gonna be alright. But yeah, so yeah, last semester this is my 6th time doing this math club thing, and last time I've been talking about like the history of math, relationship between industrial revolution and mathematics. And this time we're like looking at a big guy, which has revolutionized algebraic geometry, if you like that field. Okay,
Next you should have slide that thing off the top right. So
oh, it's working. So yeah, so we're gonna talk about first of all about his childhood and parents, then his life as a student, and then we talk about what did he do, what makes him so famous, like makes him so legend, like why is he looks like a god in the math community. Yeah, so he has a lot of story. So first of all, let's so Grothendieck, he was born in Berlin. I think he's kind of German. And then he got fostered in Hamburg because his parents are like very politically radical. They always got into prison or got banished to Russia. His dad is a Jewish anarchist, so yeah. And his mother is a writer, so that's kind of give us an idea. Like there, he's from an intellectual family and very radical. And then during the war, they're like moved to a camp in France. So it has affected his childhood because he lived in a camp, and yeah, that level has undesirable people, and they don't have state because he was born during the war. He was not German. He don't have a paper as German, and he's not French. So he has no state. And I think I remember like he used to travel around the world. He used those visa called. Do you know what the visa for stateless people back in the 30s? I haven't. Oh gosh, is that the name? Yeah, and then in during the war, it is 1942. His father were deported to Auschwitz, and because he's always doing his politics, so and he got his baccalaureate in France. So baccalaureate is the high school diploma for French system. So I think I got this like 10 years ago.
The Nansen passport.
Huh?
The Nansen passport?
Oh yeah, the Nansen passport, that one. So Nansen passport is like if you don't have state, but you need to travel around or you need to go to different countries. But the Nansen passport expired in 1938. So unfortunately, we cannot use that anymore if you don't want to be affiliated with any state. Okay, so yeah, so he was a refugee in France, and he almost spent all of his time in France in a camp, and he studied there. That's all. So this is baby Grothendieck, and with his mom. Oh, so cute. Yeah, I believe that would be a brilliant man. Yeah, so there are like a lot of stories, but we cannot talk about it. Like if you like on YouTube, Faye tells a lot of story of how he grew up. Like his teacher really liked him because he's like into things. Like he's always asking questions. about the foundation of whatever he does. He didn't like literature. He only likes math. I mean, I think he didn't like biology too. Like he only likes math. And oh yeah, I think I make a little jump here because one of the story kind of depends on his story when he's in college. So first of all, I'm gonna tell a little story about measure theory. So measure theory is like theory about length, of how to measure length in the general space. And there was like a problem with that. We have like a story where Riemann integral that has defined before to just to do like how to find the the area below any curve you have, but here it has limitations. And with and Jordan's content, or I think it's called Piano Jordan. He did some work about measuring the area, but it still has a problem like it's not stable under countable onions. And then there comes this guy Borel who finds some kind of like how to do algebra with sets. So this can be matter later. And after that, we can define a notion of a function set, but describe that of any abstract set. And there comes the bag who define this measure. We call it the bag measure, and that is the rigorous definition of length that we have right now, but describes all the measure theory, probability, and I think anything around like dynamical systems is depends on this field called measure theory. So this is a really big one. Yeah, so what we have from what Lebesgue did was, yeah, so the story is not about Lebesgue, but what he did was like he transformed the notion of length into abstract one, and now it's about like when you work on trying to measure length, you work on a function set, which is mathematically beautiful. Yeah, this is when he's cooking. Yeah, so first cooking the measure. That's what it does. I use ChatGPT to get that picture. I just get his face and I prompt like anything. So cooking. Okay. Let's go. Okay, so back to Grothendieck. So yeah, after the war, he got his baccalaureate. He went to Montpellier. That's a university in France. It's still there. I know a lot of people study there. Maybe Jessica knows the university. Have you been there? No? Yeah. And he still lived with mom. Lucky him. Yeah, but what happened is like he likes foundation. So what he did is like he was wonder about the theory, but described length and volumes and the general concept. So independently, he did the research about that. He reconstructed all the major theory by himself. He didn't know the existence of what the Lebesgue have done, but he didn't know that. But the work has been done before because he was still like from high school to college. So yeah, in this collection called Recoltissime, that's 1,000 pages autobiography he wrote. I don't know how he did it, but I'm still reading that. I'm like in the 252 pages now. So it's a lot of time. So he said like what was this satisfying to me was the absence of any serious definition of length, area, and volume. So it's like he doesn't care about formula, but he's like trying to understand the foundation, like what is the definition of length in general? That's his question, which is pretty impressive for a student but just got out of high school. And he was a little bit disappointed when he learned that Lebesgue has done the work before. But yeah, but he was kind of happy because he knew how to do the thing. So yeah, talking about politics, here it is in Vietnam during the Vietnam War, where where the French army is fighting in Vietnam. He went to Vietnam to teach the Vietnamese. So he's like, yeah, she's like kind of sauce for the government. Like, oh, this guy's not And because of him, the category theory in Vietnam is now very strong. He had a student there, and now they're like doing a lot of algebraic geometry stuff. And he become bold. Oh, that's better. He had a hair before. So, yeah, this is like what happened in the mathematical community during this time. So there was this Henry Carton seminar that he attended, which talked about algebraic topology. That's how we got introduced to algebraic topology. So yeah, I think Carton is really famous mathematician and one the huge one. Then yeah, that's how we got introduced to all the big mathematicians in the time, almost all the French mathematicians, and that's how we met Jean-Pierre Serre, in which is a very big person in algebraic geometry and algebraic topology. He's still alive, but so old and still gives the talks. And from that, he worked with his advisors are Laurent Schwartz and Jean Dieudonné. And so Laurent Schwartz is the guy who defined distribution but used in probability and functional analysis. If I'm not wrong. Yeah. So Laurent Schwartz is the guy that formalized distributions, and Jean Dieudonné is the guy that started with had done a lot of work on algebraic geometry and what else? I think he has done a lot of work. Yeah, I forgot, but those are the big people of 19th century. And then so just to test Grothendieck, he is a PhD student. Laurent Schwartz and Jean Dieudonné gave him like 14 open problems. And I think it's like he took a month to solve everything. So Jean Dieudonné and Laurent Schwartz have spent years about those problems they didn't solve. And Grothendieck solved it first. So they're like really impressed. Like, how did this guy do that? Nobody knows. And then he did his thesis on topological tensor products and nuclear spaces. So tensor products of what? Yeah, I thought read his thesis. It's on tensor products of Banach space, which is hard to read. I don't like reading it. I don't understand anything. But and then he was trying to work on sheaf. I'm gonna say like this is gonna be his, one of his important work. I'm gonna talk about this, why it's so important. So yeah. So what is the difference between Grothendieck and Jean-Pierre Serre, which is among the two biggest mathematicians of the 19th century on algebraic geometry, precise, not like on all the math. So on Recall de Semé, Grothendieck tell a story about he sees Pierre as cracking the problems with a hammer. So if a problem is like a huge stone, Grothendieck is like cracking it with a huge hammer. So his brain is like a huge hammer to open the problem. Well, Grothendieck is a kind of guy that he dip it into the acids, but lets the stone dissolve by itself. So that's how it works. I mean, he told the story. Like he doesn't like going towards the problem. He like generalize it first, and then try to find some relationship before solving the problem. Yeah, so that's all. Like Jean-Pierre said, is like he controls the examples, special cases, technical details. Really good at that, and he wrote this. I think it's coherent algebraic sheaf. This is French. This is special coherent algebraic sheaf and related work, so that you really understand all the details and and the mathematician who knows how to keep a general theory honest. While Grothendieck is like he pushes things as broad as possible, like he like generality, and he used like he developed this thing called abelian categories just to treat cohomology, which was the thing, but all of the algebraic geometry tried to use as a tools back then. But yeah, he he loves Pierre because he used a lot of his work. So yeah, their correspondence like changed the field. Like they have this. I think there's a book about their letters. I just like read like 2 hours ago. It's really amazing. A lot of description, explanation of what's going on. But yeah, to go further about what the work he did, we need to know about this guy, the Ray, and ships and use cases. So this Ray has a really interesting story. So he developed ships in prison. So he got captured in the 1944. That was like the Second World War. Held at this prison where German government imprisoned people, and then he was from fluid mechanics, very interesting. Changing towards algebraic topology. Like I don't know if anybody has done any fluid mechanics. How can you change to algebraic topology? I have no idea. But there must be some problems that make him questioning the math and then developing a new math. So yeah, he in captivity developed the ideas that led to sheet cosmology and spectral sequences. And after 1945, those methods got remarked by Cartan and Jean-Pierre Serre, and then Grothendieck who used it as to develop the theory. So what is a sheaf? So the idea of a sheaf is like you have, think about it, like trying to use like data. You have a local data, but it has nothing to do with each other. Then those local data, you try to glue them to each other. Like you have, think about space, you have this space, this space, this space, and then you glue them all together. And sheaf is the theory, but makes the glue possible. So that's the idea of sheaf. Oh, this is the is I don't know what he's, but say he's a topologist now, so he's dealing with a locally compact school. Yeah. In question, you can feel free to ask questions if you have. Okay, as I say, so what did sheaf change when we had sheaf? So we have the local pieces of a problem. I mean, sheaf now describes something general, like abstract. We have like local pieces of open sets or data or whatever, and then those pieces agree on some intersection. Then you can define like a global compatibility of all the pieces, but they have to agree at some point. So that's the idea. Like a sheaf theory is when locality stops being a weakness. Like when you did function, you remember you have like local maximum, local minimum, and those are not really. I think it's relative maximum. Yeah, relative maximum and relative minimum, and those are like just at a given at a small space, and they may not be the global maximum, and we still like have a problem with that. But now locality within the sheaf has become like very important object. Yeah, so yeah, just a sheaf is not just a gadget, it is a disciplined way of passing from fragment to the whole. So we usually have the whole and divide up the big one into small, but now we have a technique of reconstructing things from small to big. Good. So what Grothendieck did is what makes it really important. Like the classical topology is like we have space and then we have opens. Like if we talk about R, then opens are like open intervals, open intervals. So we have those open, and yeah, a sheaf of those open is like you have open covers, and a sheaf is like to glue those covers together. But what Grothendieck did is he changed it. Like those are like small enough. Like what if we define, since this covering things is a mapping from the like an inclusion from this open into the big space. What if we like just consider like kind of a morphism, like a function, and we define like a fluid functions. And by doing that, he defined something called site. And site is somewhat generalization of this property of open covering. So that's what a site does. So now what Grothendieck is like open sets become only cases of a more general notion of covering. So yeah, that is what lets sheaves and cohomology work where ordinary topology is the course. So now Grothendieck defined the notion of the shift into channel. He moved shift from like a only for topology to work for some nice category. So now people use shift in graph theory, in algebra, and I've seen some people using shift in engineering. Do you remember that? Yeah, like people use shift in engineering. That's pretty impressive. Like when you learn shift, you don't think that it can be applied somewhere because it's so abstract. Because of this work, Grothendieck make it really useful. Yeah, so the consequences of Grothendieck work is space becomes relational rather than merely point based. So when we study space, we start from points. That's the most important thing, is points. Like X is somewhere there. But now with Grothendieck, space is not points anymore. It's like more of a lattice space. So that's why we call it relational. And its descent it's representable, really cool, and then it's functorial. So we say functorial when you have like a relation but preserve composition between functions. That's what you call functorial. But I mean, it's like throwing the category. And now geometry is allowed to choose the covers it's actually need. So you can, because now the covers is more arbitrary, you can make it happen because of work with morphisms, not with opens anymore. And yeah, the consequence of those work, we're able to define what is the homology. I have no idea what is that though, but I know what is topoi. I've been working on that's a kind of an example of topoi is set, the theory of set. So sets, the category of sets is a topos. So yeah, there's a big fight in the international in the community of category theorists. We call it topoi or topos. So yeah, I always choose topos. But anyway, and we have now a lot of cohomological tools. So Grothendieck works make developed a lot of tools in geometry, topology, and number theory, and it helped to solve veiled conjectures. So I remember I looked at the conjectures, but I have no idea what's the meaning. But it has been solved. It's among the big things, and I think because of those definition, Grothendieck he received the what is the prize for mathematician? I forgot. Able. Able. Fields medal? Yeah, Fields medal. I think I Fields medal. I think this is the year they choose the new Fields medal, right? Sorry. Yeah, and it's gonna be. I know it's in New Jersey or somewhere like that. Philadelphia. Oh, Philadelphia. Yeah, this year. So yeah, that's very much about Grothendieck, and those are like the reference. You can just type on Google Grothendieck and they're gonna put you up like yeah. So this is the book that I read, the first one. He wrote it and he is explaining how to define the idea, how it grew up, like his story, and whenever you think about math, like what's going on in his mind. As I say, it's 1,000 pages, like literally 1,000. And this is it. The advertising. Yeah. This is him, I think, before he died. So That's about Grothendieck. Any question or interest? Yeah.
I heard about sheet theory. What is it exact? I never
Huh?
I never heard about sheet theory. What is it exactly?
So sheaf theory is like, yeah, you can think about it. It's like cutting and gluing in mathematics. It's like a system of how to glue some pieces in math, like how to glue mathematical objects. So that is sheaf.
Isn't it like every day where like you have a lot of small pieces, but they have to like overlap?
Yeah.
And then like you draw a cross, and then like wherever you draw a cross it has to be the same on all the sheets underneath. The sheets are like individual pieces that you put on.
Yeah, that's yeah. Yes.
I was interested in like the book that you showed for like how easy it was to read the first book that you showed, and that's one question. The second question, like, how did you choose? Like, what interested you in all of those work? Like, is it related to your research or like what caused you to go and read those books?
Yeah. So probably I got the second question. So it's not really related to my research right now, but he's just among the guy who put some foundation on category theory, and I'm working on category theory. So I used to like history of math, like where this is from, why they define this like this, and that's how I got to Grothendieck. And I was like, when I saw his name everywhere, any books about category theory always there's Grothendieck going somewhere. So I'm like, what's this guy? What's going on with him? And people always say he's the one of the greatest mathematician of all the time. I think some people wouldn't agree, but I wouldn't say he's greatest of all the time too. But he is among the greatest on the 19th century. I would say. Like 20. I know. 20. Yeah. And the book is, I think it's more poetic than mathematical, because it doesn't contain any, even like, I think the first 200 pages you wouldn't find any equation at all. It's just like stories of what's going on in his mind. So yeah, we can go to the math. Here, this. Oh, one more. This one down one more. Oh. Yep. Do you want to team up to do the math, Jeopardy? It's not a lot of question. It's gonna be hard. I need to know how many teams we have. That's how the puts the teams. So what do you want to do? Like
We're a team.
you're a team.
Yeah.
Okay, we have one.
How big do you want the teams to be?
Huh?
How big do you want the teams?
Let's make it at most 5.
Let's
Teams.
be it.
Yeah.
Yeah. We'll all be it.
Okay, y'all be team 1, and y'all back there be team. So, you'll be team, like at the end. Okay.
We're gonna have to write stuff down, or?
You just answer. So Jared, can you look at who's raising the hand first? Because you don't have the click button, please.
Sure. So what are the teams?
So 3, all of you.
Just 5.
Okay, yeah, that's good.
Wait, are we gonna write? Are we gonna write anything now?
Oh, you don't have to write. Okay.
You 5, you 3. Then we're in the back. Yeah, that's 3.
Oh, you did? No, I like.
So we're gonna have 4 teams.
So check out.
I'll name you team 1, team 2, team 3, and team 4.
That's the last part.
Yeah,
The last 2. That's not, no, the last part. That's specifically the last part.
So
yeah.
here's the rule. Anytime I ask a question, I give you 2 minutes to think. And if you got it right, you got the points. If you got it wrong, I take off the points so that you might get negative.
I thought it was.
Why are we looking at how quickly people are raising their hand?
Huh?
Why do you want me to watch how quickly people are raising their hand?
Because
First.
who raised the hand first?
But when are they raising their hand?
Huh?
You said they had 2 minutes to do the problem.
That's the upper bound.
Yeah.
I feel like we have all of it.
So only the team who gets it first will get the point.
Yeah.
Okay.
Yeah.
Like we raise our hands first, we get it all.
Really
We have
They do this on my quiz. I thought you said I'm sure.
Oh, yeah, it's the problem you gotta work it out.
No, we don't need.
You already give it, that's okay, don't
Okay. So
raise your hand.
We don't need. No, we're not.
okay, so I'll give to team one the first. So whenever you got the question right, you can choose which topic you want.
Bruce, you wanna say a little bit of the background of this game, like where it came from and where it's played?
So
It's a
I don't know about the background though, but
Started in Southeast
yeah,
in 2003.
is it?
Yeah, at the conference we went to, that's where it started.
Oh,
Jeopardy.
yeah, Jeopardy.
The math Jeopardy.
Yeah, so I didn't know that.
There's also there's a math professor from LA that was on Jeopardy on Monday.
Yeah.
And Bill wants to.
Oh yeah. I saw it. So I saw this game at the last conference I went, and it's so competitive but so fun. So I'm like,
It's 2003 and it's gone national. It's at Math Fest and it's all over the country now. But it was started by Ron Taylor in Georgia.
yeah. So that's really awesome. So we're in the Southeast. Let's win this game. Okay, I give team one the first choice. Then after that, whoever got the answer right got the choice of choosing the question. So okay, team one, which one do you want to choose?
Can we do Office 300?
Office 300. Okay, so Office 300 is ready. Whenever I stop talking, I start the timing. And whoever raised the hands first, that's gonna be, if you got it right, get the points. If not, then take off a point. Okay. So this is the room number of the grad student lounge in E section. And this is the number of terms needed for geometric series 1 plus 2 plus 4. So the sum of 2 power n to have partial sum 2 power 101 minus 1.
So what's adding to 100? Is it 100 terms? So also even 100.
Yeah, it's in each section, but you're almost correct, but it's not 100. So you're not, yes?
101.
Yes, it's 101.
No, it's not.
Yes, it's 101. So,
Okay, thank you.
You have to answer this part of the question.
what is 101? Yeah. Okay, so team 3, you choose the next.
That's
You choose the next question.
I was just trying to work.
Which one? Mathematician 200. Okay, ready? This British mathematician helped to break the.
Alan Turing.
You.
Who's Alan Turing?
And which team is that?
Team
Team 1. Okay, team 1 got it. The answer is who is Alan Turing?
Sorry. Well, you gotta read that. Just reading the question. Wait, I'm
Raise your hand. Raise your hand so I can see it.
Yeah,
I just want to like slap the tape.
yeah. Okay, so now it's back to you. You pick them. Okay.
You guys want to go? Mathematician 300, please.
300. Mathematician 300. Okay. Let's do this. Ready? Ready? This French mathematician gave his name to the criterion.
Criterion of convergence behavior and sequence metric.
I think it was wrong.
Okay, Ross.
Cauchy?
Oh my god.
Who is Cauchy? Yep, correct. That's team
My
two.
first pronouncing.
Okay, now
Yeah, think about it.
you have the choice. Which one?
Mathematician 5 one.
Mathematician 500. Ready? This Clemson University mathematician worked in algebra. Rhetorics and discrete systems.
It was team 2 again.
Team two.
Who is Matthew Macaulay?
Gonna say a lot of post
All right.
Wait until he finishes reading it.
Yes, I read it. So that's what I.
So you have this deal. Choose
Mathematician 400.
okay, mathematician 400. Ready? Known as a modern prodigy, this UCLA mathematician won the Fields Medal in 2006 and famous for work across analysis, number theory, and combinatorics.
Terrytown.
Who is Terrence Step? How? All right. Now you're back on track. Yeah. So team two is still leading with 100 points. 800 points. Team one 300 and team three 304. Okay. Now you choose the question.
Let's try systems 200.
Systems 200. Okay. So
Yes, please.
yeah, if 3x plus 2y is 267
You're right.
and x plus y, this is what is the value of x?
7. What is 67?
What is 67? I don't think so. Yeah, that's not at 67. Yeah, you need to. So I give you 2 minutes to figure it out and.
Double the second equation.
Oh my god. Yes. What is 67? That's on me. Sorry.
That was a crazy question.
Yes.
There's an entire category of 6, 7 last weekend at this conference.
Oh.
Yeah, so I was like, yeah, so like it's not yet the 67.
Let's go one digit of
Yeah,
just a
you
7.
got it.
How we roll through this.
So what is 67? Okay. Now next one.
Wait, you choose.
Yeah, true.
Let's go The Office 200.
The office 200. Okay. Ready? This is number of the well-known April's office, and this is the 14th partial sum of 1 plus 2 plus 3 plus like sum of n. Okay, we have right there.
Is it O? What is it? O112?
What is 112? Are you sure it's not? No, it's not. It's not 112. Yes.
What is 105?
Yes. Got it right. What is 105? So that's April's office. So all one door is the office where everybody where we have a meeting, not
No,
different
it's
office.
like mentally searching the catalog.
Yeah.
You tried to
And
I don't know.
Square is 225.
Oh, yeah.
okay. Team one, you choose the question.
And choose 2. And so first, like, what is that plus 1 and then what is that minus 1?
Figure out.
Oh, me again?
Yeah, you got this.
Systems 300.
Systems 300. Okay. This number is the smaller of the two real solutions of the following system. Something team
Yeah.
4. Yes. Team 4. The smaller. It asks for one number. Which one? Pick one. 2. Correct. What is 2?
Yeah. No, right.
Okay, now you fix the question.
Why? Replace it. Come on, bro.
Office 400.
Office 400.
Plus 3.
So Office 400. This is the number of the office in Martin, right in front of a color printer. So there's a printer, color printer, and it's given by the 51st term of the sequence AN, in which the partial sum satisfies Sn is n squared plus 5n. Yeah, you can write it down. It's easy to confuse. Yes, I give you so give it 2 minutes to solve it, and if not, then nobody get a point. So
Actually, no.
yeah, if you're like you have a print something in Martin Hall, and where the color printer is, you just in front of that the office.
I don't like numbers. So I don't like numbers.
Yeah.
Or
What is 108?
No, it's not 108. Yeah, I'm supposed to take it from team 3. Yeah, we have 50 seconds to solve it.
actually it should have brought this stuff.
Or use one iPad.
No, I didn't. Sure.
This uniquely, I don't think the sequence is technically uniquely determined by this property.
I think it is like there's a bit difference.
Oh. I was misreading something. Never mind. Of course, it does.
So if you know the relationship between sequence and its partial sum, it's really fast to compute. 10 seconds? I don't. Yeah. I mean,
That's a good question.
right.
It's not.
Okay, we're done. So
Oh my God.
So what is it? So the office is for just the one next to April, because that's where where is what is 106. Yeah, so to compute is like A 51st is just S 51 minus S 50. So you just change 51 and minus 50 of the difference of the two, and you got the
Blue brain.
Yeah, did not read it last time.
it's the difference of the two partial sum of n and n plus 1 or n and n.
I know this, it was, yeah.
Yeah, so
We just like.
who got it correct before? Oh, those are the people, but team 3. Team 3.
Thinking.
Okay, team 3 or team 4?
Or, I'm
Oh,
sorry.
so you still choose. The office one. It's the number of team's office in long haul computed by the 34th term of arithmetic sequence 1, 7, 13, and 19. So we got here.
What is 250?
50. Nope. Sorry. You are doing close though.
What, how we in there?
So the first term A0 is 1, A1 is 7,
Okay.
A2 is 13,
Oh,
and A3 is 19. So it's gonna be the 34th. And it's arithmetic sequence.
Okay, wait, starting at 0. That's what I was saying.
Yeah, start with 0. Okay.
I knew that. Yeah. Because plus 1. There every day. This is 0. First wait,
So you have 1 minute and 30 seconds.
What? 211.
No, it's not 211.
Okay, so it's not.
It's okay.
Not your fault.
Maybe it was. Thank you for trying to.
Okay, any?
Oh, whatever.
Oh, we can't answer it.
Yeah, you can answer unless you.
What is 205?
Yes. What is 205?
Yeah.
Team two got the points.
So what you did?
So team two is still leading. Yeah, Chief's office in Bangkok is 205. Yeah, if you have like tennis office hours.
I just know.
So now team two, you choose the next question. We still have.
The office 500.
Okay.
Yeah.
Yeah, this is the hardest of the section, so let's. This is the office number of grad students in the third floor of Martin Hall and given by the value of the infinite series sum of 51 n squared divided by p power n. Jared.
That was team 3.
What is on 306?
Let's check. What is 306? Yeah. Well, that's their office apparently. That's my office. Yeah. That is.
How much the best?
And that's Jared's office too. Yeah. Now team 3, you choose the question. Mathematician 100. So this is a 96 fields medalist, revolutionized algebraic geometry with ideas such as schemes and talk about homology.
I think team 2 had their hand up like.
You raise your hand immediately, so
Before
before we
it's
read it, so let's go through who it is.
Okay, so it's
Whoa.
Wait,
who goes first?
you get 2 minutes.
Who is Grothendieck?
No, they should.
Right.
It's not.
Yeah, we're trying to raise their hand immediately and then just figure out who it was.
Well, I was you get like 5 seconds to answer once you raise your hand. I feel like once you call on, right?
Yeah,
Took 5 seconds to figure out who it was.
still don't have all the tools to measure everything. So team 2 got 1,000. So now team 2 choose the next question. Everything is about system stuff, so you need probably to write
It's not
something.
over. Everyone can still win until after this question.
And there's gonna be
Final Jeopardy?
there's a final Jeopardy. Don't worry about that.
Systems 100. You guys gotta get all these stuff.
Systems 1. So
Systems 100. So
you can.
yeah, you ready with your pencil, your system. In the system x plus y 24, x minus y 10. This is the value of x.
4,
Actually,
3.
17. What is
What's the answer you say?
17?
Yes. What is
You add them into
70?
It's probably
No, I set up a matrix and then I wrote.
So now it's just the question.
You heard it. You can't you know.
Oh no, I'm not that smart.
Yeah, now it's just the question.
Gotta draw the line.
Oh,
let's do systems for 400.
400. Systems 400.
Wait,
There is the larger real solution of the following. Yeah, the larger solution of the following system: x plus y 8 and x squared plus y squared 50.
Team 2.
Team 2. Yeah.
7, right?
Damn.
7.
What is 7? What is 7?
you didn't give us our points from the last
Oh,
question.
my bad.
Oh, okay.
So yeah.
Wait.
Psychologically,
Out of 100, right?
yeah. So now you're 700.
Yes.
Okay. I will. I mean, yeah. Thanks for.
Because we get the daily double, right? Is there in that?
Yes.
There is in
Yeah.
the Math Jeopardy.
So now the last question. No choice anymore.
Is the daily double?
Yeah. This is the deal. Okay. What's the deal? For the nonlinear system, x squared plus y squared is 5, 9, and x times y 2/9. Every real solution has coordinates whose sum equals to this number. So you got the solution, you add them up, and that's gonna be the answer I'm asking for. What is it? Yeah. Team 2.
This game. Yes, 1.
What is
What do you want?
1? Correct. Yes. So we have team 2 dealing with 1900, team 1 with 700, team 4 with 300, and then team 3 with 100. So that's and it's the hope is not lost. We're gonna have to find. So for the final question, I'm gonna give you papers. You're gonna write the solution down, and you need to write your bid. Like the maximum bid again is the number of points you have. If you have 1900, the maximum bid you can is 1900. You can make less than it, and if you're correct, your points gonna be that's gonna add up to your points. If you're wrong, then I'm gonna remove that from your points. So yeah. So your limit is your points there. I'm gonna team 2 bid 501.
That would be so dope.
Write down your bid, and the answer gonna be with there. Right, your bid.
You guys are saying that all.
Your bid.
Can we do
Well, actually, if we bet nothing, we finish second. We finish second or better.
Well,
we bet.
okay, that's true.
Oh, no, I don't bet it.
This is like spread out perfectly so that.
Now, what-
Okay, I think sometimes you get the big. Yeah.
The scores are all like, you know,
Yeah.
double.
You ever see the music queued up? Final Jeopardy.
Oh,
Google Jeopardy music.
Nobody's nobody's incentivized to win anything. That's true. The dominant strategy is for everyone to win 0.
I don't have faith in our ability.
Nice, right up.
Zero, that is here.
If we bet.
No, that's true.
You're actually betting 6-7.
So like 20 something.
No, you gotta do the final, you do the Jeopardy music.
Yeah, sure,
Oh.
let's go 6, 7. Yes.
This one.
The theme song.
Final
Jeopardy. Final Jeopardy.
I know, yeah, so you gotta make it like.
I looked at the
like
definition.
Yeah.
That goes though.
this. This is what you eat.
You just sing for us.
Because you're trying to.
Yeah, it doesn't
That's.
God forbid.
No, I don't.
You haven't done your whole.
On break.
So once I'm done with that song, I'm gonna ask the question. Everybody's ready. Are you supposed to be at this very Yeah. Okay, if you already got it.
Okay, yeah, we got it.
Not bad.
You're supposed to play that well.
Okay, now you're ready. I'm gonna ask the question now.
Yeah.
So everybody's has wrote down their bit.
Yeah.
Okay, you wrote down your bit. Okay, awesome. Let's do it. Oh. But let me remove this one for a minute. I don't want it to end this way. The number of steps in the stairs between M and O section of Martin Hall, from first floor, I forgot to write down, from first floor to the third floor, the number of steps you need to take to go up is given by the fifth term of the following recursive sequence. This one. Yeah, I know that's a walk up. Yeah, if you walk up there every day, you don't need to do that. It's not, you need to compute this. You need to write it down, write down your solution. I'm gonna give you
Which floors again? From the
from the third floor to the third floor. Fall from the first,
Ground or first?
Ground, you just did it. This one,
This one.
yeah, first to third. And given by,
how long do we have?
Okay, from now, we want to run by 30 seconds.
Yeah.
So you do the computation, so write down the solution, and I'll take it after 1 minute and 30 seconds. Yeah. That's Jeopardy. So the fifth term of this recursive.
I think this is how I'm trying to bring it. They know it's how. Yeah. It's close.
You have 30 seconds to solve the problem.
Yes, that's right.
You want to write it down? You have 15 seconds.
We should specify which ones.
That's what I think it is.
Specify our insurance, yeah, they're not super far.
10 seconds.
Yeah.
5 seconds.
Well, your system.
Okay,
So
you gotta write.
Okay, we are done. I need to collect the answers.
I have
Okay.
yeah.
Answer.
I could not have pictured you.
That definitely counted there. I think a lot, but that was.
I go up.
Oh,
Alright.
okay, so we have one team who answered, who got the answer correct. And that is team 1.
Yay.
Yeah, it's what is 48. I need to write it.
Good job, what you got?
We had it on the bat. Our wager was the 400.
Oh,
Oh.
my bad. It's mixed. Which one is the wager at? Okay, team 2 got it correct. Team 3 got it correct. And team 4.
Pretty cool.
I didn't compute it, so it's not correct.
Oh, can you compute it? Maybe it's the right answer.
The idea is you compute it. So going back. So the bid of team 4 is 100. That means I need to take 100 from your points, but you have 200. For team 1 did 6, 7, but yeah, actually. But I add 6, 7 to your points, so you have 767. For team 2, your bid is 499. So if I add that up, that would be 2399. And for team 3, your bid is 50. So that'll be 150. So the winner is team 2. And now I just remember I forgot to buy the price. But, yeah.
All right, thank you guys for coming. Let's thank Fabrice one more time. Make sure that there's no pizza left over and have a good weekend.
All right, thanks, man. Oh, thank you.
Every year they play this at there's a local conference. Next year it's going to be at Georgia Southern. 2 years it's probably going to be here. If anybody wants to field a team and go, like, please let us know. That's something that it'd be cool to bring some students, both grad and undergrad.
Well,
I think it. Yeah.